I'll need that. Right. Need that. Okay, welcome back to Thursday's lecture. And how is everybody? Enjoying week 1? Yeah, great. So today we're going to discuss data definition language. So we will talk about 3 types of data models in this course. The first one is the ER diagram. So ER diagram is basically a sketch you make when you are presenting your idea to your boss. So your boss didn't get a PhD, didn't get a CS degree. So he has a business to run, and he talks about all of the data he has. But now you need to build a database for him, and the first stop is you make a sketch of the structure of the database. So this is usually, like we call things like this, the schema of the database. So a schema is basically how you define the data will be stored in the database. So we can call it the data of the data. So as you can see that we're planning to have a student table, maybe we'll have a unit table, and they're connected using the enrolled in table. Maybe we'll use a table, maybe we'll not use a table. So this is the first step when we are designing a database. And the second, usually, the second data model we will introduce is the relational data model. We'll talk more about that in next week. So basically, it's a middle stage between ER model and SQL implementation. So the relational data model will be like a couple of boxes, and then each box will be the head of the table you create. And then you have a bunch of arrows pointing to each other, indicating the primary and the foreign keys. And then the last one, which is the most important one, the actual schema in SQL. So we'll emphasize on the ER diagram, and today we're going to talk about how it can be converted to SQL right away. And in the next week, we'll talk more about there is a middle state called relational data model, and then we'll talk more about the systematic way to convert an ER diagram into the SQL implementation. And as you can see that, so from the last lecture, I made some demonstration over here, and hopefully I'll have some time to do that as well. So the purpose of first week is that you need to get familiar with the VxDB02 environment. This is super important, and we can see that there are students still having issues accessing this server, cannot type their password or some things like that. You need to address this by the end of this week. And I have created, I might be the first one who have done it. I made a video about based on practice exercise 1. So each step by step, so that should help you with the basics in VxDB02, as well as setting up PostgreSQL server, little tricks you can connect to the server more easily, stuff like that. So you need to get that done hopefully by the end of the week, and after that we can move to actual SQL code. So, in this week and next week, we'll be talking about data modeling. So basically, we need a way to describe what information is contained in the database. So we need to describe the relationships between the database items, and we need to define the constraints on the data. So when you move to week 2, when you're doing the exercise, you see that constraints are super important, because we need to make the database, as we mentioned in the last lecture, we need to make sure that database is a logically coherent representation of the truth. So how do we make sure that is logically coherent? We need to make a lot of assumptions on the database. For instance, we need 7 digits for maybe the ID, and then for text file number, we need 3 digits, dash, 3 digits, dash, 3 digits. So we have as humans, we have a pretty good idea of what a good data look like, but SQL doesn't know that. So we need to translate our human language into a way that the database management system understand what we want when we are defining the schema and when we are inserting data into the database. So, the easiest way to model data is by describing them in human language. So start simple. We need to, so basically, if you really go to the workplace, this is where you need to talk to, you need to do a lot of talking to people. You need to talk to the front end people. You need to talk to the business people. You need to talk to your boss. And you need to have understanding what is required of your database. And so here's an example. So let's say we're back to the .com era, and we're building Instagram again. So these are the decisions that we need to make before we actually talk about ER model as well as SQL data definition language. So we need to talk about, like, given an application, given a scenario, given a business model, what are the things that concern us? So mostly we're concerned with the nouns, so basically the entities, as we'll discuss later, as well as the verbs. So what are the data items involved? So that will be the nouns. And what are the relationships between these data items? So that will be the verbs. So student is a noun and is an entity. Lecturer is a noun and is an entity. And lecturer teaches student, and teaches is a verb. So that verb captures the interaction with those two entities. So these are the things that we care about when we are designing the database in the very beginning. So this is an example. You could in Instagram, I'm sure everybody has an Instagram and play with Instagram, and the Instagram schema can get a lot more complex than this, but this is just a straw man approach. You should have users, you should have posts, and you should have comment, and you should have hashtag. And remember remember on Monday we talked about a Justin Bieber effect. The reason why Justin Bieber's, his Instagram made the database crash is because they used to have an extra entity called like. So like is a separate entity in their database. And whenever they like the Justin Bieber's post, they create a new row in the like table, and then they will have to count all of those tens of millions of rows to get the number of likes. So as you can see that these are the entities that we are interested in. And then based on these entities, after we write down all of the entities, all of the nouns in our business, then we can talk about the relationships between them. And for relationships, we need to care about two things. First is how many entities correspond to how many entities in this relationship. Second is, are these entities totally participating in the relationship, or they can not participate in that relationship? For instance, as a lecturer, sometimes I teach courses, sometimes I don't teach courses. I'm on break. So in that sense, I don't totally participate in the teach relationship. And these are the requirements you can modify. You can make assumptions about in the early stage of the database. And here we can assume that in our database, we say that user creates posts. And we can assume that a user can create more than one post, which is basically the world we live in. And then the post can only be created by one user. So you don't really, in this case, we're imposing the constraint that a post can only be created by one user. And between users and post, who do you think has total participation in that relationship? So if you're a user, do you have to create a post? No, right? There's always a friend who doesn't post anything on Instagram, and he always follows a bunch of strange accounts on Instagram, but he never posts anything. So it means that for user and creates, user that does not totally participate in that relationship, and that's important. That will be reflected in our later design choice, in our code as well. And for a post has to be created by somebody, cannot just come out of nowhere. So post in this case should have total participation in that relationship. So these are the small details, small requirements we need to think of. So we need to think of the entities, relationships, as well as cardinality ratios, as well as whether the entities are participating totally or partially. So user follows user. So this is a many-to-many relationship. And user likes post. Well, a user can like many posts. I like many posts every day. And a post can get more than one. A post can get more than one likes. So these are the things that you should keep in mind when you're starting to design a database. We'll get to the actual terminologies and notations. So other constraints you might want to impose to your database might look something like the username must be unique. So, and all of these constraints, they don't really, we don't just put them there so that you can see it. All of these constraints, they happen because back in the days, somebody created a database where username is not unique and then created a problem. And after that, they decide, okay, from now on, this field needs to be unique. So all of these requirements, they may come from passive experience, they may come from your boss, they may come from your colleague, but these are the constraints that we write down and we want to implement in SQL. So a username must be unique, of course. A user cannot follow themselves. Yeah, that makes sense. Every post must have exactly one creator. So this is the correct constraint you make. But obviously, like right now on Instagram, they have a mode called collaborate. So obviously, you can collaborate with another artist and then make a mixed post or something. So this is not, I think this is no longer a constraint. So basically, you need to get the nouns, the verbs, and work out the cardinality ratio in those relationships and whether they fully commit to the relationship. So these are the things that we care about when we are designing a database. So, we're not gonna go through that in class. You can think of it when you're at home, like if you want to design Gmail from scratch, like what are the entities you might want to consider, what are the relationships you need to consider, and the cardinality ratios, and whether those entities totally participate or partially participate. So maybe you could have like, of course you need to have users, you need to have emails, maybe you need to have attachments. So give it a thought, and you could probably post that on the forum and discuss this. So yeah, this is the straw man approach. This is not the only way of doing it. And also you can think of what kind of entities are in the UNSW handbook. So the courses is an important entity. What else is an important entity? Course offering is an important entity, because the same course you could have different offerings. You could have 2025 term 2, 2026 term 1, and we can also, like what else do we have in the handbook model? Like anything else? Like any entities or relationships that we have missed? I haven't looked at the handbook in a while, so I wouldn't know. So what other entities are there in the handbook? Let me Google it.
Maybe like the faculties.
Faculty. Can you give an example, like Faculty of Engineering?
Yeah.
Right. Yeah, that could be it. Handbook 2026. Ooh. Okay. Well, by faculty, thank you. And they also have like area of interest and the subject area, And our faculty is engineering and computer science, and then every bit of detail of this could be an entity in the back end. So like without looking at the back end, like learning outcome could be a multi-attribute, a multi-valued attribute in a database. So without looking at the database, we wouldn't know, but from a design perspective, areas of interest, faculty, subject area, they're all legitimate entities to think of if we were to design the handbook from scratch. Okay, thank you for telling me that. And now let's jump into entity relational data modeling. So this is the real deal. So the world viewed as that we have talked about is interrelated entities. So entities have three major. The ER diagram has three major constructs. So from the name, you know that entities are important, relationships are important, and there's something else is important. So attributes. So we need a way to describe these entities as well as relationships. So we can define, okay, this table we're going to store students, this table we're going to store lecturers, but we need to define these entities in some way. So this is a, well, students, we don't usually, what are the good features of students, attributes of students that we might be interested in? ZID is a attribute, but it is not a very important attribute because later on we'll call it the key attribute because it is a unique identifier of students. What are other things that people are interested in? Well, students' marks, students' in study level, like postgraduate or undergraduate or higher research degree. I think in UNSW they call it HDR or something, higher degree research or something. Or like the year in which you enrolled. So all of these can be attributes of a entity, and relationships are just recording the association between entities. So ER diagram is basically we have an agreed notation convention like this, and then based on those natural languages, like based on those requirements, our job is to translate that into a sketch like this so that it becomes self-explanatory. So when you're presenting your boss these, well, he might be interested in that too. So send them both. So send him the natural language description of the database, and if they're busy, then just send them that. So the ER diagram is a self-contained description of the schema of the database. So basically, just by looking at the schema, just by looking at the ER diagram, we know that what entities are there and what relationships are there. So basically, squares are entities, diamonds are relationships, and circles are, or ovals are attributes. So that's the easiest way to learn ER diagrams. And it gets slightly more complex than that, but that's the most important deal. So rectangles are entities, and diamonds are relationships, and ovals are attributes. And we also have like double rectangles, double diamonds, and double ovals. They represent slightly more complex things. So we would have something like a weak entity, a identifying relationship, as well as multi-valued attributes. So we'll talk more about that later when we encounter them. So right now, the most easy ER diagram, we can just, all you need to know is that rectangles are entities, diamonds are relationships, and ovals are attributes. So here, this is an example of a bank, of a schema of a bank. So how many entities are here? So how many entities are there? 3, right? So we got branch, we got account, we got customer, and how many relationships are here? Relationships, 3 relationships, yeah. So in order for us to create good database schemas in SQL, we need to do this. We need to be good at this at first. And those ovals, they're all attributes. So for branch, it has a branch ID. So maybe this is just BSB for banks in Australia. And it has a name. Maybe it's called Kingsford branch. Maybe it's called, I don't know, Balangaroo branch. And for account, it has count number and balance. So for the attributes that is underlined, that's called a key attribute. A key attribute is very important because this is the unique identifier of this entity. A key is super important in database cores because we'll encounter key attributes in ER diagrams, in relational data model, in the SQL implementation, and in the later part of the course, when we talk about normalization theory and concurrency control, the key attribute is something that we cannot get around with. So key attribute is super important. So basically, it is a unique identifier of the entity. So for students, it's your ZID, and for people in the United States, it's probably their social security number. And in the banking scenario, their account number is the account number is the key attribute for account, and for customer, the customer number is the key for customer. So as C, and so this is another slightly more complex ER model. So here we can see that we got a slightly more complex construct of attributes. So we got attribute with attributes. So this is what we call a composite attribute. So a name, and then a name has a family name and a given name. And favorite food, the reason why person's favorite food has a double oval is because this is what is called a multi-valued attribute, because obviously people are human beings are so complicated. We have too many favorite foods. We cannot just pick one. So my favorite food is Chinese, Italian, and maybe Turkish. So you see, so I have 3 favorite food, and if the value of the attribute is more than one single thing, is not atomic, it cannot be put into one cell in the Excel spreadsheet, then it is a multi-valued attribute. So, which means that you should never put 3 things separated by comma into one cell. So that is a very bad practice. So at this stage, we just know the existence of multi-valued attribute, and later on we'll discuss how do we model them in SQL. So relationships are hard, and well, not in database cores, relationships are not hard, but in real life, relationships are hard. In database cores, we're mainly talking about the relationships with 2 hands. So we only talk about the two-way relationships, like only 2 parties, only 2 types of entities are participating in this relationship. So we make this easy, because in real life, like two-way relationship is good enough. Like you could have a case where you have a 3-way relationship where you have another arrow pointing to another entity. So that's out of the scope for this course. So if we only talk about 2-way relationships, then by considering the cardinality ratios and participation constraints, these are the some of the possibilities that we can see. So the first one, if the relationship is many to many, so basically no constraint. Many to many, many students can take many courses, and the course can be taken by many students, then we don't draw any arrows here. And if one part of the entity has a cardinality of 1, for instance, a car can only be owned by one car owner, and but a car owner can own more than one car. In this case, we need to mark the one cardinality side using an arrow. So here, basically, this means that a car can be registered to only one car owner. And when we have a thin line, it means there's no participation constraint. And when we have a bold line, or in some cases, in some lecture notes, you see a double line, then it means total participation. So basically, in the first example, it kind of assumes that in order for a student to be a student, he must be enrolled in at least one course. So otherwise, if you don't take any courses, you're not a student, and you need to be, I don't know, you need to be kicked out of the university or something. So that's basically what it says. So a student must totally participate in some courses. While a course, you know, if a course is out there and nobody takes it, it is still a course. Well, it may sound strange, but this is the underlying statement. This is underlying assumption this piece of ER diagram is telling you. And for the second one, we have total participation on both sides, which means that a car needs to be owned by somebody. It needs to be owned by at least one person. And then because here we have an arrow, which means that a car can be owned by exactly one person. So not two people, not 0 people, exactly one person. And then a car owner can own more than one car. And so to start with, a car owner can own more than one car, but because the car owner also has total participation, so a car owner has to own some cars. He can own one car, 2 car, 3 car, but he cannot own 0 cars because the car owner has total participation. So that seems, sometimes it seems strange, but sometimes that's the choice they make in the database to make their data internally agreeing or consistent. And the last one, the person and the UNSW driver license, this is a one-to-one relationship. So on which side they have total participation? A person does not need to always have an NSW, New South Wales driver's license, but a driver's license needs to have somebody associated with it. That's why on the driver's license side, we have total participation, which means that in semantics, it means that a driver's license has to be owned by exactly one person. But on the other hand, person has partial participation, so a person can be associated with 0 or 1 driver license. So he can have 1 driver license, or he can have 0 driver's license, and he cannot have 2 because this is a one-to-one relationship. So now, okay, I hope you get it at this point. So now what you're going to do is that you need to describe the semantics of the following relationships. Like, can you do that? Can anybody want to try? Anybody want to try the first one? Okay, you can take some time to look at it and then just, if you know the answer, just raise your hand. Yeah.
I think the first one is like partial relationship between like lecturer and the course.
Right, partial participation, exactly. Yeah.
That's because the lecturer does not need to teach a course, but a course has to be taught by him. Something like that.
Yeah, in this case, it indicates that a lecturer doesn't always need to take the course, and then the course needs to be taken by how many lectures?
I think this one's
Many to one relationship. Exactly. So in many to one, because on that side there is an arrow. So this is a many to one relationship. So it means that a lecturer can teach 0 or 2 courses, whereas a course needs to be taught by at least 1 lecturer. But it could be 2 lecturers, 3 lecturers, 4 lecturers, 5 lecturers. And what about the second one? Want to give it a try? Second one is, you don't have to explain, but because these things are just created to be there, but it sometimes doesn't make sense because this is a assumption, you know. We don't really have a case where we have like multiple lecturers teaching the same course, maybe in the last offering of this course, but usually we don't have that. But these are just like assumptions of the database. Like you want to give it a try the next one?
The second one's like a many-to-many one.
Yeah, many-to-many one.
Each lecturer must teach like multiple courses, and each course must have like multiple lecturers.
Yeah, a lecturer needs to teach at least one course. At least one course he can teach. So this is a many-to-many, but many can also be one, right? But because they have total participation, they cannot be zero because lecturers need to teach at least one course. It could be 2, 3, 4, 5, 6, 100. And then the course needs to be taught by at least one lecturer and could be taught by 2 lecturers, could be taught by 100 lecturers. This is a many-to-many relationship. And the last one is the easiest one. So you want to do that one as well? Yeah, it's a one-to-one relationship, and
So it's like one lecturer must teach one course, and one course must be taught by one lecturer.
yeah, something like that. But you want to take into consideration the participation constraints indicated by the bold line. So the course must be taught by exactly one lecturer. And the lecturer, how many courses does a lecturer teach? 0 or 1, exactly. Because lecturer, they had partial participation, and because this is one-to-one, so lecturer teaches 0 or 1 courses. So it is possible that in this case, the lecturer does not teach any course. Okay, so we have more practices, so we don't have to worry about not getting it in first go. And yeah, so these are the explanations. You can look at them after class. And this is another exercise. So is this the schema that we have looked at before? So basically, this is a ER diagram of the university, probably. So this is probably the handbook schema. So we got students, and we got units, and we got schools. And can anybody give examples of entity values? That's a tricky one. So I'll start with an example. So what it wants from us is that we want to present them the examples of the values of entities. So basically for unit, I'm going to do an easy one, and I'll leave the hard one to you. For school is an entity. How do I describe the entity values? Well, I just describe the values of the attributes. For school, the key attribute is the name, and then homepage. So basically, the example of this entity is computer science, School of Computer Science and Engineering, comma, and then the CSE website. So that's the example of the entity value. And a student, it could be like Jerry, and then my ZID, and then Kingsford, Sydney, Australia. Okay, can anybody give another example? You want to try? For the I want you to try the unit one. The unit one. Can you give an example of the values of this entity? This could be a bit tricky. Yeah. Pardon?
Code and semesters, are those the main ones? The main attributes for unit?
Yeah, code and semester, those are the key attributes for unit. So unit, as you can see that it is a little bit weird as it has like two key attributes. So in this case, their combination is the unique identifier of the unit. So you want to give it a try? Yeah.
It could be 3311 and semester 1 topics could be SQL, faculty, will be database.
Right. And I noticed that when you said topics, you mentioned SQL and Python, right? Right. So that's exactly what it looks for. So you mentioned the code of the course, you mentioned the semester of the course, and also you mentioned the topics, because this is a multi-valued attribute. And in this course, we have multiple topics. The SQL is one topic, and Python is another topic, and title is basic database systems. Yeah, that's exactly what we look for. Thank you so much. And so basically, this is a summary. Entities are basically the objects of interest in the scenario. Relationships are associations, and attributes are the property of entities. And you'll see that they are a very useful step towards an actual SQL schema that hopefully we should get to in the end of this lecture, as well as in the beginning of next week. And okay. So this is let's go through this exercise together to give you an idea of how to build an ER diagram from scratch, and then we'll take a break. So, and in the postgraduate course, I think this is what they do in the assignment 1. But in our course, we're more coding based, so it's more about the SQL implementation. So what usually is done is that we give you a description of the schema of the database. So we're telling you that we need to build a database for a university enrollment system. And we're telling you that we need to model students. The student has a unique student ID. So every little detail in these words they matter. And they have a name and an email address, and course has a unique course code. So whenever you see unique, then that is a giveaway for the key attribute. So because course have a unique course code, which means that the course code is the unique identifier of the course, which means that that's the key attribute. That's the primary key of the entity. And so those are the only two entities. And the relationships, we care about enrollment. Students enroll in courses. And as you can see, what about the cardinality and participation constraints? So it says a student may enroll in many courses or none. So maybe partial participation. A course must have at least one student enrolled and can have many students. So a course must have at least one student enrolled. That's very important. That's a giveaway for total participation. And each enrollment has a mark and a grade. And this is important because a mark or a grade, a mark and a grade, they're basically like integers or text, right? And they're also attributes. But where are these attributes attached? Can they be attached to the student, or can it be attached to the course? Or like where should we attach this attribute? So I think let's just start building it. So the first thing in building the first thing when you're building the ER diagram is you start with the entities. So students and courses, they are the entities. So two big rectangles. So students and courses, no biggie, very easy. And then we attach the attributes to them. So right now, student has a unique ID. So that would be the unique identifier for the entity, so that would be the primary key. We underline them. Course has a unique course code, and we underline them as well. At this point, it's super easy. And then we add the remaining attributes. They also have name and email and title and UOC. So these are all very simple attributes. So if they tell you we need to record students' favorite colors, then that's a multi-value attribute. You need a double oval. Or we need to record a student's age. So age is a tricky thing because age always change. So in databases, whenever we want to record something that's changing, we don't really want to create a separate column for that, because what we end up doing is that we update that every year, right? Because in 2026 I'm 31, and then in 2027 I have to increment everybody's age by 1. So that's very redundant, and that's very abnormal if you know what normalization means in database. And we'll come back to whether that's a good thing or a bad thing, but right now we just have to understand that things like age, they're called derived attributes. See that? Age is a derived attribute, and you got is a dashed oval. So in derived attributes, in our relational database, we don't really model them. Like, we don't really model them because they're not needed. Because we can always compute age from the birth date. So age is more like a query than an actual attribute. But sometimes, in the Justin Bieber case, we talked about it makes sense to create a separate attribute. So in that sense, we're actually denormalizing the database. So that is a trade-off. But in good old relational databases, what we consider normal is we don't put the derived attribute in the database at all. So age is a good example of derived attribute. Can anybody give me another example of derived attribute? So basically, a value that can be computed based on other attributes, and it could be changing.
Whether or not they got like distinction, high distinction, and that one, like,
Pardon?
like their grade, that could be like another. Like
Yeah, exactly. Yeah, they're great. Because if we record people's marks, then there is a fixed mapping from marks to grade. So if you're 86 and it's HD, if it's like 49 is a fail. So makes no sense to record the grades separately. So grade is a good example of derived attribute. That's a very good catch. I actually forgot that. And add the remaining attributes, and then we add a relationship. The only relationship we mentioned here is students enroll in courses. So we start by a good diamond, and then we look at the cardinality constraints as well as the participation constraints. So a student may enroll in many courses, and a course have at least one student. So this tells us that this is not one-to-one, this is not one-to-many, this is a many-to-many. So at least we can get the cardinality right. This is many-to-many, and there's no arrows on the hands. And let's look at it more closely and look at whether students or courses have total participation or partial participation. So student may enroll many courses or non-courses. So that looks like no. A student can be on a break and he doesn't take in any courses, and that's a partial participation. So a thin line over here. And a course must have at least one student enrolled, or it doesn't make sense for us to call it a course. So in this case, it's a double line or a thick line. In this case, this is a total participation. So this is how these ER diagrams are drawn. And in the end, we put the marks and grades associated to the enrollment, because these are relationship-specific attributes. And I think I do agree with him that grades should be modeled as a derived attribute. So yeah, I think, and when we put them all together, it looks something like this. So we got entities, relationship, attributes, and we underline the key attributes. And for now, it looks all right. And maybe in the second half of this lecture, or in next Monday, we'll talk more about like the more complex scenarios where we have a weak entity and where we have, yeah.
I'm just trying to understand the arrows more. If you said
Yeah.
that, like, if you said a student can only enroll in one course, where would you draw the arrow for that?
If student can only the student can only enroll in one course, then we should draw the arrow on the course side.
So pointing
Wait. A student can only enroll in one course, and we draw the arrow on the student side, because if we draw the arrow on the course side, it means that, yeah, what did you say?
You got it right. I'm just confused about the errors. I'm wondering like where it goes.
Yeah, if a student can only enroll in one course, then we should have the arrow on his side.
And it points into the enrolls.
Yeah, it points to the student. It always points outwards. Okay. Yeah, the arrows, they always point outwards. So it never points to the relationships. Okay. And for the purpose of this course, it makes sense for us to understand how to construct these ER diagrams, but also it is more important for us to know how to map them into SQL. Yeah?
Can you explain why grade is a derived attribute?
Oh, grade, like here, I should have modeled this as a derived attribute because grade can be computed based on your mark. So it's redundant information. So your mark is like 49, then grade is automatically fail. And so that's basically redundant information that we don't really store. Because in the database theory, what they consider normal is they want at least, they don't want redundancy in a normalized database. So this is what they consider normal. And if we have redundancy in the database, then this is denormalized. So they call it, so they have an idea of normal databases, and they have an idea of denormalized databases. And in this course, we need to learn the normal ones first, and then maybe you know why sometimes denormalized are good too. Okay, let's take a break for 10 minutes, and then we can come back to more ER models and maybe how to map them to SQL. Yep.
Now one question.
Yeah, sure.
What if I make this arrow point towards there?
We don't ever do that.
Okay, so how would I make it if a person has to get a license? Has to get exactly one license?
One has to.
Yeah.
So if has to, then that's total participation, and we make this line thick.
Okay, like this one.
Yeah, like this one, just like this one. So we just basically copy that and then put it here.
Like this one.
Like this one is a bolded arrow. So you see that? So we keep the arrow, and it's also bold.
Okay, so this one means everyone can get a car?
This one is a magnitude 1.
Okay, like multiple cars can be owned by the
Yeah,
one.
yeah, multiple cars can
And
be
if I
owned
make
by one
this
person.
thick, then every person has to get a license.
Yeah, every person has to have a license to become a person,
Okay.
and then every license has to be owned by a person. So that's strictly 1-to-1.
Oh, okay.
Okay.
Okay, thank you.
Hi.
My name is Tanisha, and I think
Hello.
I emailed you
Yeah,
about my prerequisite waiver.
yeah.
Okay, I think you said that it would not be possible for me to actually do this subject.
I think it's hard to do that.
Okay.
Yeah.
I genuinely think I can because I've done a little bit of databases in high school.
Uh-huh.
I made a whole database. I had ER diagrams. I'm like used to databases.
Uh-huh.
And there's also no other subject that I can actually do.
Okay,
So it would like, if I fail, then that's on my own accord.
okay.
So do you think you could like?
We'll talk more about that later. I think I already did the. I think I already talked to the student inquiries about
Yeah,
that.
and I went and talked to them, and they said if you approve it, it's fine.
Okay.
Okay.
We'll talk about that later. Okay.
Can I just send you an email and then you respond?
Yeah. Send me another email. Yeah.
Okay. Yeah.
I'm just going over this again.
Yeah, sure.
So this is saying that a car, an owner can only have one car. If
This
there's going into it.
it's because this is a magnitude 1.
Yeah.
So a car can own many. Car owner can own many cars. So this is a
But
magnitude 1.
I thought you said that if the arrow goes into something, then it would mean it can only have one of them. Like for the student.
Oh, so if the arrow goes into something, it means that this entity's the cardinality is 1. So the car owner is 1. So one car owner corresponds to many cars. And then,
So for this one, if a student can only have one course, why would it go into the student?
A student can, so one student can go only,
Can only enroll in one course.
so that would be a one-to-one.
Or no, or let's just say let's say a course can have many students, but every student, they can only enroll in one course. Would that still be a one-to-one?
That would be a many-to-one.
Yeah.
Because a course can have many students, and then a student can only take it in one course, so it's many-to-one.
So where, in that case, where would
Many
the
to
arrow
one, then we put the arrow here, many to one,
go?
because
So put on the right side. Going
yeah,
in forward.
because the way you phrase the sentence is like the students can take it in one course, but if you really think about it, for the courses to participate in that relationship, the course's entity is one.
Okay.
So that's why the arrow is pointing towards the entity one, the cardinality one entity.
Okay, so the car owner can have, it goes into the car owner, so the car owner can have many cars, but every car, it's pointing this way, it can only have one owner.
Yeah, exactly.
Okay, cool, thank you.
You just mentioned that we have you make a video for set up the SHH for the.
Yeah, I made a video about that.
Where can I find it?
I think I made a, yeah, I think I made a notice, basically here,
The home.
yeah.
Oh, okay.
So I put it on here, and so basically,
Yep.
yeah,
Oh,
yeah,
alright.
yeah.
Also the relationship. So N to ones mean like the car owner, one car owner. No.
And to, so this is basically, you can think of this as many cars correspond to one car owner.
Yeah.
So
So one car can only have one car owners,
yeah, but a car owner can have many cars.
but we also can have many of car owners, but we didn't show that, right?
What do you mean? Yeah, in this case, we didn't show that. In this case, this is a many-to-one relationship. But if you want to make the case where a car can be owned by many car owners, then that would be a many-to-many. Then that would be more something like this. So this is a many-to-many, and then we got both on both sides. So a car needs to be owned by at least one person, and then one person needs to own at least one car. So it is total on both sides, and then is many-to-many. So more like a biparty graph if you think about it. So cars can, so it's more like you get what I'm saying? Like more like a biparty graph, like on the left-hand side we got cars, on the right-hand side we got car owners, and then we got like edges.
Yeah, a lot of line.
Yeah.
And when do we need to show that error?
We only show the error when the cardinality is one. So like in the cases you talked about before, we don't show the error because it's a many-to-many. If it's many-to-one, we show arrow pointing towards the one entity.
Yep.
So sometimes when you listen to semantics, you get this and you get this wrong. But the easy way of doing this is you think about this entity and how it participates into this relationship. Is the cardinality one? If it's one, then the arrow goes in there. So you can say that many cars can be owned by one car owner, and then after saying that sentence, you don't really know where to put the arrow, right?
Yep.
But you need to think about, in that case, many cars are owned by one person, then the car entity, when they're participating into the relationship, their cardinality is many, and the car owner, the cardinality is one.
Yep.
So it's many-to-one, and then the arrow points
The
to
arrows at one.
the one entity. Yeah, exactly.
And so for the thin lines, it's like the
Partial.
number of participants there is 0 or 1.
Yeah, for thin line, it means that whether it can hit 0 or not. So, yeah, basically, if a person could have 0 or 1,
We can use
then
the partial participant.
yeah.
And how about the total participants? Is 1 to more?
So basically, when you think about cardinalities, by default, it starts from 0 to infinity, right? And then if it's 1-to-1, then it becomes 0 or 1. And then if it's total participation, then it becomes 1, because it needs to be exactly 1. Because if you got total on both sides, which means that is both sides should have larger or equal to 1. And then since this relationship is 1-to-1, which means that both sides need to be less than or equal to 1, which means that the cardinality is 1. And do you get what I'm saying? Like you need to work this like step by step, and like by default they're all from 0 to infinity. And if you have an arrow pointing towards it, then that range becomes 0 to 1. And if the arrow is bold, then it's exactly 1.
1-to-1.
Yeah, 1-to-1. If the arrow is not bold, then it's 0 or 1, because it could be 0.
Get it. Thank you.
Weak entity. Map the course entity, map the many-to-many, add constraints. This is complete. Complete Instagram design decision. In your style. Okay, let's get back to class. So a student asked me where do they get information about the practical, it's basically, you can find it here. I posted it on YouTube. So I'm planning to do more videos so that based on previous courses, based on the feedback of previous offerings, one thing that they would want to see more of is more demonstration, more interaction with the database, so that it can potentially help you with the assignments as well as the final exam, because the majority of the assignments and the final exam will be coding based, and makes sense to be strengthening the practical component of the course. And yeah, it's basically here, if you in case you didn't know. Okay. Yep. So this is a completed ER diagram, and this is the ER diagram based on the informal Instagram model. So we have media, users, comment, genre, and then some attributes and relationships. What do you think is missing from here? This was created a while ago, and do you spot anything strange with this ER diagram? I just realized it. It's missing a very key component. It's missing a very key component of ER diagram. Yeah.
The search keys.
You mean the keys? Yeah, exactly. That's what. Yeah, the key. One thing that's missing is the keys. So the key attributes are missing. I mean, they're not really missing, but they're not underlined. So this is clearly, this is kind of like a bad example. We never create an ER diagram where we don't specify what the key is. So for users, the key should be the email, and for comment, it should have its own key, and for gener, it should have its own key, and in that way, every entity in the database has a unique identifier. So this is like a rough sketch or something that people will have hard time converting this into SQL implementation because they wouldn't know what a key is in this case. And well, in the case where you don't, like, what should you do when you don't know the key of an entity? What is the very common practice if you have seen it in real databases? What do? They just put an ID on it, right? So for users, we just use email because emails are supposed to be unique for each user. And if for other entities we cannot find a good attribute that can act as the key, then we can just throw an integer on it and we can just call that an ID, and then that assigned integer will be the unique identifier of that entity. Okay? And another thing that we need to talk about for ER diagrams, as well as how to convert them in the future, is we need to talk about the cases where we have subclasses and the inheritance. So basically, as you can imagine, when we're talking about entities, not all entities are created equal. Some entities are basically, they can inherit the attributes of other entities. So that's what subclasses and inheritance are. And this is how inheritance work. So example 1, we have, it has only one subclass. So manager has only one superclass, and employee has only one subclass. In this case, we just put is-a. We just put is-a here. And then this shows the inheritance of these entities. So basically, all of the attributes, inheritance means that all of the attributes associated with the superclass, they are inherited by the subclass. It's kind of like C++. Like if you have the parent, object, and then you have the children objects, and the children will inherit the attributes of the parents. And in a more complicated case, a superclass has more than one subclasses. Then we need to talk about whether these subclasses are overlapping or disjoint, as well as whether this inheritance is total or partial. So in the disjoint case, the two subclasses, they are mutually exclusive. So let's say the superclass is person, and then subclass 1 is students, and then subclass 2 is lecturers. I'm not sure if that's the case. Well, you cannot be the student and the lecturer in the same time. If that is mutually exclusive, then we put D here. And what if, I'm a lecturer here, but I might be a student in UCID, I might be a student in UTS. And in that case, the two subclasses, they're overlapping, and then we put O over there. So we put overlapping. One example is I think it's in the hospitals where sometimes they make it like the nurses and the doctors, they're mutually exclusive. Obviously, if you're chosen to be a nurse, you cannot be a doctor anymore, and if you're a doctor, then you're not a nurse. So in that case, most likely this is exclusive. And for partial or total, it means that if it's partial, then we put the thin line here. If it's total, we put the thick line here. If it's total, then it means that all subclasses of the superclass are listed here. There's no default humans in here. And if it's partial, it means that there could be other subclasses that we haven't listed here. So let me give you an example. So here we got the parent class to be a person on the left-hand side, and then it has partial participation, and then it's broken down into doctors and patients. And doctors and patients, yeah, they're definitely overlapping because doctors get sick too, and the patients, they could be doctors. So the doctor and patient subclasses, they're overlapping because we could have doctors that are patients. And the reason why we have partial participation is because doctors and patients are not the only people in the world. We have other people, we have like plumbers, we have lecturers, we have electrical engineers, stuff like that. So in this case, we only put a thin line over there indicating that these two subclasses, they're not the only examples of the parent class. And sometimes in the company, maybe you want to be more strict. You want to enforce that all of the employees in our company are either full-time or part-time. So you make a very you make a distinction over there, and in that case, you can enforce it like a total participation. So in this case, this usually happens in a company's database where everybody is an employee. Steve Jobs, he was an employee of his own company. He got fired from the company, by the way, but that's a different story. Sam Altman, he's an employee of his own company. And Bill Gates was an employee of his own company. And all of the companies, they can be divided into permanent or contract. So in their company, they make this distinction that you're either permanent or contract, and you cannot be something else. There's no middle ground like what. So basically, there's no casual workers in this company. You're either full-time permanent or you're contract. And distinct here, so you put D here means that these two subclasses are disjoint. So you cannot be a permanent employee and at the same time you're a contract employee. So basically it is forbidden in this company. And this is another example of subclasses and inheritance. So I think this happened to me when I was, so everybody's in UNSW, they should have a ZID, and ZID is the unique identifier of everyone in UNSW. And name is our attribute, is an attribute, and maybe we have other attributes. And here here students and lecturers are subclasses of person. So because we're all people in UNSW, and here we make it clear that a student and a lecturer, they are not overlapping. They are disjoint, meaning that a person cannot both be a lecturer and a student in the same university. Maybe UNSW that's the case, but I'm not sure if that's true for other universities, but that seems generally the case. And note that we put the thin line over here in the inheritance part. We put the thin line over here indicating partial participation, meaning that in this database there could be other subclasses of people who are not students or lecturers. We got plenty of those people in university. And then we got two relationships, and we got course entity as well, but we already know how to model those. And here's an interesting thought experiment. This could get pretty hard. I need to refresh myself. So how do you modify this? Let me make it more. How do you modify this ER diagram of class hierarchy if we want to satisfy one of these requirements? So the first one says, what if you want to make some people in the database? We want to make some people. We want to make some people in the database. They are students or lecturers. So here, when we say students or lecturers, in computer science, or means or and end. So it's weird. And like in real life, or means like almost means XOR, XOR, but in computer science, or means it could be a student, it could be a lecturer, it could be both. So what if you want to make it some people in the database are both students and lecturers, or one of them? Well, in that case, we want to change disjoint to overlapping, because those two subclasses can now overlap. And then what if we want to make all people in the database are students or lecturers? So here we mentioned all people. So we're making it very clear that everybody in the university is either a student or a lecturer or both. So if you see or over there, it means A or B or both. If you see exclusive or over there, then it means A or B, but not both. So what if you want to make all people in the database are students or lecturers or both? Then we should indicate that this is a total participation. So everybody in the university is either a student or a lecturer or both. And in the third one, all people in the database are students, exclusive or lecturers. In this case, because we're making assumption about all people in the UNSW, then we need total participation. We change that to a thick line. And then also, we're saying that everybody in the university, they are either students or lecturers exclusive. They're mutually exclusive. In that case, it should be disjoint. We just keep disjoint over there and change the thin line to a thick line. Exactly. And in the last example, some people in the database, they are students or exclusive or lecturers. So in this case, I think this is the case we're representing right now. So we're making claims about a part of a group, a part of the UNSW people. We're not making claims about everyone. So this is a partial participation. And then they are either students or lecturers. So basically, this is a mutually exclusive case. So we put disjoint over there. So this is basically the ER diagram right now. Okay, that could be very tricky. And another thing that's important in ER diagrams, yeah, sure.
Would there ever be arrows between a subclass and a superclass, or no?
No, we don't have that. And that's a good question, because arrows are usually used when we have like one-to-one, so indicated one cardinality, right? So in this case, when we put it like this, is almost we always have at least two subclasses. When there's only one subclass, we just use is a. So this is kind of like the arrow case, so where it only has one subclass and then it only has one subclass. These are all just notations, and the important thing is to understand what it means for the data, and so that you can correctly implement that in SQL. And another thing that's important is weak entities. So weak entities, so we should discuss weak entities and identifying relationships together, because they're tied together. When do we have so every entity, if it's a double rectangle, then is considered a strong entity. The difference between a strong entity and a weak entity is that a strong entity, like all of the normal entities, they have their own primary key. So employee has a social security number. So that's pretty straightforward. And for a weak entity has a partial key or a weak key, or something is called a discriminator. So a weak entity has a key of its own, and it needs an identifying relationship to exist in the database. Think of the example where we have employees as well as their dependents. in the database. So for instance, you work in a company, you're very important to the company, so the company, you're viewed as a strong entity in the company, so you should have your own employee ID. If you work in UNSW, that employee ID is ZID. But if your wife and kids are also stored in the company website database, they're not as important as you, so, but we still want to record them in the database. So they have their own partial key, and they should be dependent on you to exist in the database. So for instance, for a weak entity, its primary key is the combination of the primary key of the strong entity that it associates to, as well as its own discriminator. So in this case, the contact makes more sense. Each employee has maybe a bunch of contacts, but in the database, the unique identifier of the contact is not the contact name, because maybe employee Jerry has a bunch of contacts, and they're called Mark and Alice, and Mark and Alice would be their discriminator of the contacts. And maybe someone else, maybe, so Jerry had 2 contacts, and then Tom had another 2 contacts. And they may have the 2 contacts of the same name. So Jerry has Alice and Bob, and then Tom also has Alice and Bob, which means that the discriminator may not be unique. So for us to uniquely identify the weak entity, we need to combine that part with the primary key of the strong entity that it associated with. So basically, when we're talking about these contacts, we're saying that this is Jerry's Bob, and this is Jerry's Alice, and this is Tom's Bob, and this is Tom's Alice. In that way, if we combine the primary key of the employee as well as the contact name together, then only then we can uniquely identify a weak entity. So that's what a weak entity is. Kind of, it's kind of complicated. And as you can see from the identifying relationship of a weak entity, so it is a double diamond, indicating that it is an identifying relationship of a weak entity. So this is called an identifying relationship. This is called a weak entity. And then look at this. This is a many-to-one relationship, because the strong entity can have many weak entities as dependents, but the weak entity needs to have only one, it needs to have exactly one corresponding strong entity in that identifying relationship. So the weak entity is always drawn like this. It needs to be one-to-many, and then it needs to be partially and totally participation, and total participation. And in SQL, there's a couple of rules when we convert ER diagrams into SQL. The first rule is, if you got a strong entity, make a table. The second rule is, when we have a relationship, make a table. When we have a relationship, it doesn't hurt to make a table. And sometimes, depending on the cardinality, we may get away with not creating a separate table. But if we do create a separate table, it's not incorrect. And when we have a multi-valued attribute, we need to create a table. And when we have a weak entity, we want to create a table as well. So that's basically, when you are having trouble mapping ER diagram into SQL, basically the rule is, when in doubt, create a new table. And then examine the database to see whether that table is necessary. So in this case, I've talked too much about weak entities. So basically, whenever you see weak entity, create a table for it. And for that table, the primary key should be the combination of the primary key of the strong entity as well as its own discriminator. And we'll encounter examples of weak entities in SQL soon, I think. Yeah, so this is basically ER diagrams. And let's look at a couple of more exercises. So this is an exercise of developing ER model for a hospital, I guess. So we got patients, doctors, pharmacists, and pharmacy, drug, and doctors. And we also, and based on these sentences, we can get the relationships as well as the attributes related to them, and whether or not they have weak entities, you need to really really read the description to decide whether we have weak entities. And sometimes it's a design choice. You can design them as weak entities, and sometimes you can design them as strong entities. It depends on what you do with them. And okay, so you can do them in your own time. So basically, I strongly encourage you to read this and then model them step by step. I think more interesting is the relational model as well as the SQL schemas. Yes. So now that we have talked about the ER model, and that's just one type of a data model we encounter today. Yeah. Do you have a question? Yeah. So the relational model is basically a middle ground between ER model as well as SQL schemas. And in this course, you need to really focus on SQL schemas. And we'll talk briefly about relational model in today's lecture and next week's lecture. So basically, a relational model is, let me give you an example of relational model. So this is an ER model on the left-hand side, and then this is a relational model on the right-hand side. The ER model, we already know how to create them. So we look at this description, a bunch of text. We get the entities, relationships, attributes, and then we draw a nice sketch like that. And then the reason why I said the relational model are kind of like the middle ground between ER model as well as SQL implementation is because basically when we are transforming ER models to relational model, we are now specifying and we are actually making the design choices of what tables should be there. So for instance, when we're mapping something from ER model to relational model, we need to really think of what tables are there. So for entities, we make a table out of it. And then for composite attributes, we squish them and just list them as simple attributes. And for weak entities, we make another tables. And for multi-valued attributes, we make another table. And another thing you may notice from a relational model is that it has a bunch of arrows. These arrows are here to indicate foreign keys. So a foreign key, there are two types of keys in relational database that are super important. The first is called a primary key. So primary key is basically a key. A primary key is a key, and a foreign key is a reference to another table's primary key. So every table, every strong entity should have a primary key, and when we are trying to link these tables together, we need primary keys. So a primary key needs to be referencing, a foreign key needs to be referencing the primary key of another table. Let me give you an example. So let's say accounts and customers, they're both strong entities, so they deserve their own tables. And now we have a relationship. What do we do with them? Well, when in doubt, we just create a new table for it. Well, it happens to work at this point because this is a many-to-many relationship, and in this case, it is compulsory for us to create a new table, because otherwise we cannot really rely on foreign keys to store that owns relationship. So for owns, we create a table, and then for this table, for this relationship, the primary key of this relationship is the combination of the primary keys of accounts and customers. And so basically for owns, account and owner together, the combination is the primary key of owns. And we also need to tell them that account is basically account number, and owner is basically a customer number from the customer table. So we need to make these arrows to indicate that this is a foreign key. This is referencing the primary key of another table, and this owner is basically the primary key of the customer's table. And after we transform that into a relational model, it is very close to the SQL implementation at that point. So basically, we can take every table that we created in the relational model and then transform that into a create table command in the data definition language we will learn in the next week. And maybe we'll be exposed to some of it today. So, so this is the data. So we should be exposed to the data definition language of SQL today, and we'll talk more about it next week, because this is very, very important in relational database in PostgreSQL. So this is how we can create a table in PostgreSQL. So every time, so after ER diagram and a relational data model, you kind of have decided which tables to create. And to create a table, the table name is basically the entity name or the relationship name, and the attributes are basically those attributes. And what is the most important about the create table command is the key constraints as well as those attribute constraints. So you need to specify what attribute or what combination of attributes is the primary key. And also, you need to specify what attribute is the foreign key. So basically, what usually goes here is, for instance, this is a TFN. Then we can say that the TFN, you should check that the TFN should be of the format 3 digits, 3 digits, 3 digits, separated by dashes, and then maybe the second attribute is the number of hours worked in the company. Then the constraint should say, well, the number of hours put in the company should be between 0 and 168, which is, the number of hours in a week. You cannot exceed that. And for primary key, you want to specify if it's an entity, then the primary key is basically the key attribute of that entity. If it's a relationship, then it gets slightly more complicated, and we'll talk more about how to map one-to-one relationships, man-to-man relationships, and all those relationships into tables. And whenever your primary key involves attributes from other tables, then you need to specify. You need to declare that this is a foreign key that references the primary key of another table. So let's learn about it via an example. So this is a student enrollment, and this is a university enrollment database. I think we have created way too many versions of this, but let's play with this one now. I think this is the one we played with in today. So we got students enroll in courses, and the courses are offered by schools. And by looking at it, how many tables do we need to create? Well, we need to create the student table, the course table, the school table. And what other tables do we need to create?
We need to create the tables for the relationships as well, for enrolls and offered by.
Exactly, that's a very good thought. One way we can look at things like this is when in doubt, create a new table. So for every relationship out there, if it's a diamond, if it's a relationship, it does not hurt to create a new table for it, because it is definitely one of the correct ways to model it, but it may not be the most efficient way. So for enrollment, do you think it's necessary for us to make a new table? So basically, enrollment is recording the interaction, the many-to-many interaction between students and courses. So if we don't create a table, can we store that piece of information using foreign keys? For instance, can we add another column in the student table and say, these are the courses that he took? Or can we modify the course table and then add a column, these are the students that are in this course? Do you think that's a good idea?
Oh yeah, I mean like the students table can have like a course code on, and then after that could be a point.
But the issue with that is a student is can take many courses, as you can see. A student can take many courses. Like you're taking 3 courses, someone else is taking 1 course, and then that column now becomes not atomic. You need to separate those courses in comma, in those cells, right? And that's not a very good practice. And for course, we can't do that, because in this course we have several hundred students, and then in the university database, if we put a column called students enrolled in this course, and then we have like 700 names separated by comma, that's going to be a very bad database. So in this case, having a table is very useful. We need to record every single interaction between student and courses. So in this case, enrollment, we need an enrollment table. What about offered by? So offered by is recording the interaction between school and course.
I don't think we need a table for offered by, because each course is only offered by one school. So we could have like a column for school in the course table. Would that work?
That's a very good point. So the reason why, I think he gets it. The reason why we might not need a separate table for this is because the courses, can you repeat that? The course are?
Course is only offered by only one school.
Yeah, exactly.
It's like we can have like a column for school in the course table.
Uh-huh.
And then we can make that the foreign key.
Yeah. That's very interesting. Why do you think that's the case? Do you think that's because of cardinality constraint, or do you think that's because of the participation constraints in the offered by relationship? It has to do with both, right? So this is a classic one-to-many relationship, and in this case, it is better for the course to record the schools that are offering this course, because each course corresponds to only one school. But it makes no sense for the school to record every courses that they have offered in the schools table, because imagine if you have a table called School of Engineering, School of Environment, School of what else? Architecture, and then they have a separate column called courses offered, and then COMP3311, 9311, 9313. That's disastrous. So it makes more, whenever we have a many-to-one relationship, it makes more sense to use a foreign key to store that information. So that foreign key is basically, for each course, we can store the primary key of the school that has offered it in the courses column, and that will be called a foreign key. So basically for courses, we're storing the only school that has offered it. So the reason when I said there's no harm of creating a new table is that if we create a new table of offered by, then it will just be the same length of the course table, right? If we create a new table called course by, and then it has 2 foreign keys, one pointing towards courses code and term, and the other one pointing to schools, then that is okay. But that just introduces redundancy to the database. So whenever we have a many-to-many, so the conclusion is that whenever we have a many-to-many, we always need to, it's compulsory to make a new table. Whenever it's one-to-one or one-to-many, then we can get away with using foreign keys to store that information. So if it's one-to-one, let's imagine what happens if this is one-to-one. If it's one-to-one, one course offered by one school can only offer one course. In that case, we can store that information in either tables. We can make a school column in courses to store the school that offered this course, or we can add a column in school that stores the courses the school offers because it's one-to-one, so we don't waste extra space. And when it's one-to-many, then we need to pick the appropriate side and let it store the primary key of the other side. And this primary key will be called a foreign key in this table. So basically, whenever we have a many-to-many relationship, we need to create its own tables. And the new table should have two foreign keys, one referencing table A's primary key, one referencing table B's primary key. And then whenever we have one-to-many or one-to-one relationship, then we can just use a foreign key in one of the tables without creating a new table. Yeah?
It's just like following rules like this. Why can't we use some tools like directly compile the ER diagram with the commands and like make the
Pardon, can you rephrase that?
If it's so like just following rules like this, like why can't we just write like a program that will automatically compile the ER diagram or like the code to do the procedure like this?
We can do that. We can definitely do that. That's a very good point. So maybe I should mention this yesterday. So that's completely doable, and we can do that. I want to do that so that I can make marking a lot easier. But the thing is that my teaching philosophy and my understanding of the concepts tells me that so when you want to do that, you have to use AI, right? But AI is just another extra layer of abstraction. So
Yeah, it's just like if it's so like set out like this, it's just cut and play. There's no like subjective part of it. It's just like following the rules. It's one to end, you do this,
yeah, exactly. So you're right. It is as straightforward as that. It is pretty straightforward. So
what's the point of like using the first receiver command to like create a table instead of just
the whole point of, I understand what you're saying. So is actually you're completely correct. So basically, you're asking us why do we have ER diagrams as well as SQL schema, right? So SQL schema is for us. We're programmers. We're database engineers. But ER diagrams are for non-tech people. So basically, we need to sit down with them. We need to present them, hey, this is the schema. This is the structure of the database. They don't understand the code. They don't understand SQL. So we are responsible for presenting the design as well as converting the design into implementation. But I completely agree that there is an exact mapping from one to another one. Yeah. And if you can do that, please invite me to that GitHub repo. And so I would say this is the most difficult part when mapping ER to SQL, which is deciding whether you need a new table. So if you don't want to go through the thought process, you can just remember if it's many-to-many, create a new table. If it's one-to-many or one-to-one, use the foreign keys wisely. And so basically, when we have an ER diagram like that, we have a student table, courses table, school table, as we have mentioned. And the many-to-many relationship, we need to create a different table for it. And in this table, this can get a bit more complicated than the other tables, because in this man-to-many relationship table, the primary key is the combination of the primary keys of those two entities. So we got student entity and course entity. We need to grab their primary keys, put them together, and make a primary key for this relationship table. And then because we have grabbed primary keys from other tables, we need to tell them, we need to specify that, hey, this is actually the primary key of another table, and this is actually the code in course. So whenever this happens, we need to specify the primary key as the combination of the entity primary keys, and then we need to specify where it's coming from. So basically, we're specifying the foreign keys. And you can specify foreign keys and primary keys in line, or you can specify them at the end of the create table comments. And sometimes you need to decide which attributes goes into relationships. And one thing that we might need another time where we might need ER diagrams is for things like derived attributes, because a lot of times, for instance, the number of likes on Instagram as well as grades, from the perspective of database manager, we don't like them because it introduces redundancy, and that's not a very good relational database. But sometimes that is very important to the business, to the underlying business, and is very important to the stakeholders. So we want to keep it there so that maybe they can make the judgment, we still want this in the database, and then they can we can then implement it. And in the standard ways, in the standardized method, we don't really convert derived attributes unless the Justin Bieber effect happened. And constraints, so this is where we want to make sure that the data we put into the database are good data. You'll see more of this in the practical 2 exercise, and I've already made a video about that, and hopefully you'll learn more hands-on skills from that video. So basically, for each attribute in the table, we need to make sure that it is in the correct format, and it is in the correct range, and things like that. And I strongly encourage you to read the section 5 of the PostgreSQL manual. Yes? Pardon? Oh, that's a very good question. Shouldn't we have only one primary key? Yes, exactly. Each table should have one primary key. But in this case, we're treating the combination as the primary key. So basically, student alone is not a primary key. Course alone is not a primary key. We need a combination of both of them to uniquely identify a role in enrollment, right? Let's say I want to know one enrollment, but we want to know what student and want to know what course. So we need a combination of those primary keys to be the primary key. Yes, that's good catch. And also when we do that, we need to note in the foreign key, telling them where they're coming from. And constraints. So primary key and foreign keys themselves are constraints too. And here are some more domain constraints you can add, and you can read more about them in the section 5 of the PostgreSQL manual, where you learn more about data definition language. So basically, it tells you how to impose these constraints, how to make the integers within the range, and how to make and even pattern matching. I think pattern matching is in chapter 9, where you can learn about pattern matching using like, similar to, or regular expressions. So I think regular expressions are the best choices. And here's a complete schema. You can see that courses has its own table, student has its own table, and enrollment has its own table, but we didn't really create a new table for the one-to-many relationship, and we only added the column of student's name, school's name in the course table. Okay, let me see if we have more examples of that. Yeah, and one thing about the primary key is that the primary key should always be unique. So whenever you declare an attribute or a combination of attributes to be a primary key, then it means that that attribute or that combination of attribute cannot repeat itself. So let's just say that we have already entered an enrollment data, Jerry, Z520-1685, enrolled in COMP3311, and Mark fail. And then if you try to enroll Jerry, Z550-1685, 9311 pass, then it's a violation of the primary key constraint because you have entered 2 rows with the same primary key. And another thing that the database often complains is a violation of referential integrity. Referential integrity violation often occurs when you are inserting into the table, and then that table has foreign keys in its primary keys. Let's just say that enrollment. Let's just say that you're trying to put into the database the enrollment table has student and course as the primary key, and if you're trying to put in a row of data where the student is not found in the student table, or when the course is not found in the course table, then it breaks the foreign key constraint. So basically, the database is telling you that, hey, the student doesn't exist in the student table, and the course you entered does not match any course, any rows of the course, so your enrollment data is wrong. So basically, if you enter data like that, then that would be a violation of referential integrity of the database. So referential integrity are enforced by these foreign key constraints. And let me see what else should we talk about. Okay, so I think we should get through another example and then call it a day. So this is the Instagram. Instagram example, and by looking at it, we need the media table, user table, comment table, genre table. What's most important is how we model these relationships. So has is a many-to-many relationship, which deserves its own table. Owns is a one-to-many relationship, so we can probably use a foreign key to handle that. And the same thing with posted by is a one-to-many relationship. We can probably handle that using the foreign key. So, so for the entities, we create their own tables: users entity, media entity, and genre entity. So for these entities, they don't have a natural primary keys. So in this case, we just throw in an ID. No biggie. Like our ZID is an ID. So we don't really use student email as primary keys. We use an ID, which is easy to manage. And for relationships, and for the comment relationship, because this is N-to-1, it makes sense for each comment to store who made this comment, instead of for people to store every comment they made. So whenever we have a one-to-one or one-to-many, we ask the many-side entity to store the primary key of the one-side entity to save space. And you can, of course, create a separate table to record every interaction with the two entities, but that will introduce redundancy. Okay, I think that's a good place to stop, and I strongly encourage you to read through the last exercise we have, because it introduces 3 ways of converting ER diagram into SQL when we have subclass inheritance. So basically, we have the object-oriented way, the ER way, as well as the single table way, and we'll talk more about it in the next week, Monday. Right. Thank you so much. Have a good weekend. I'll stick around if you have any questions about the course.
Hi, Jerry.
Yeah,
So,
sure. Hi.
I was basically lost during the part when you introduced the foreign key. When do we realize that we need a foreign key? Like, obviously, from the example earlier, we can have multiple foreign key for.
We need a
where is
foreign.
it?
We need a foreign key when. Let me see. This is not a good example. I think we had a walkthrough example that should be. Oh, you see that? This is where we need a foreign key. So this is an many-to-many relationship, right?
Yep.
To create a table for that, create a table for that, and then this one we need to create a table too. Enrollment, because we need the enrollment. The primary key should be student name as course title, course code. So that's the primary key. But in the table, in the database, we need to that SQL knows where are those primary keys coming from. We need to make sure that we need to declare that this is a foreign key referencing ZID in student, and another one that's a foreign key referencing code in courses.
So the foreign key here is a mark.
No. Foreign key here, enrollment should have like ZID and code combination together. They are primary key of this new table. And then enrollment, it should, ZID should references this ZID, and then enrollment code should references code here, and those two will be foreign keys.
So we have two foreign keys in this case for the
Yes.
enroll table, the table of enrolls.
Exactly.
So basically we know we are going to have them because we need to identify student and course here
Yeah.
for each of them.
Yeah, exactly.
And when we create the table, we are going to list this for the enroll table. Right?
Yeah, when you create a table, you need to specify the primary key, and then if the primary key is grabbing information from other tables, then you need to specify the foreign keys as well. Like most of the times when we're specifying primary keys, they have their own, the primary keys, this is what they're born with. And when for entities and for relationships, we create a table of their own, then the primary key are taken from somewhere else. So we need to specify where they're coming from so that we can later join them back.
Basically, the enroll doesn't have its own primary key. It has
It has to
borrow.
Yeah, it has to grab the primary key from other tables, and then later on, if we want to know the mark of a mark of you in this course, you need to join all of them together, or you can just do a query here. And let's say you want to do a query because this one doesn't store name. If you want to do a query, a person name, what's your name? Mingyuan. What's your mark in COMP3311, then you want to make a join with this, and then we can use that to find your ZID, and then we can find your mark. So that foreign key is there so that we can join things back.
The foreign key is also used when we want to create a query to track down.
Yeah, that's the sole purpose, to join tables back in together. Okay. Hey, hello.
Hello, we don't have a quiz this week, right? So what are the expected to complete by this week?
I would suggest work through this week. I suggest you do the week 1 practical exercise and work through the examples of lectures.
Okay, and what can we expect to solve in the quiz?
Pardon?
What can we expect to solve in the quiz? Will it be like queries or theory questions? Or?
You see that quiz should be pretty straightforward.
Okay.
Yeah, as long as you. Yeah, quiz are the easy part of this course. Basically, they're basically giving away the.
So
quizzes should be.
end of this week, just get the VXD set up and do the practice exercise 1.
Yeah, that's super important. Okay. That will be number 1 priority.
Thank you.
So I'm thinking for USW and this diagram, grade isn't actually a weak attribute since it's not only concerned with marks, but also it could be also related to stuff like attendance and yeah. So
What do you mean?
and a low attendance could also cause a fail, right? Yeah, like stuff like that.
Oh, I
Yeah.
gotcha.
Yeah.
Oh, okay. Yeah. So it's not a one to, it's not to mapping. Yeah.
It's
Yeah, if
not-
you put it that way, like the double hurdle or attendance,
Yeah,
then
yeah.
in that case, this is not a derived attribute. I understand
Yeah,
what you're saying.
so-
Yeah.